All right, as promised, here are some answers for today's review. We'll give you all these and you can check your answers with these. And then on Thursday, we'll get another review in. I'll post another answer video, and then we'll take the test on Friday. All right, so here we go. Number one, if you jumped in the air 3 times, what might the elevation versus time graph of that story look like? Well, it's going to depend on how quickly we jump. It's going to depend on if we kind of pogo stick back into the air without staying on the ground for long, or if we gather ourselves and jump again. So it's going to be a height probably measured in inches, and it's going to be an elevation in inches, and it's going to be time probably measured in seconds. So I can label my axes accordingly. So I'm going to have my independent variable is going to be time, and I'm going to measure that in seconds. And then I'm going to measure elevation over here on the y-axis, my dependent variable, elevation, and I'm going to measure that in inches. All right, and then it just depends on how high I jump, what my scale is going to be. Well, I'm not feeling like putting a whole lot of effort into it, so I'm saying probably a 3-inch jump is going to be pretty close, Bill Lambier style. That's a way outdated reference, but anyway, 1, 2, maybe 3 here. So that'll be my max height. And then just a period of seconds. So 1, 2, 3, 4, 5, 6 seconds, maybe something like that. So I'm going to complete my graph by saying it's going to take me 1 second to jump to 3 inches in elevation and then land back on the ground. And then for 1 second, I'm going to be on the ground before I jump again. So if that's the case, about halfway through my jump, I'll be at my 3-inch mark. So my jump's going to look something like this. Oh, close. Where I quickly gain elevation at the beginning, but as I get to the top of my jump, I slow down until I reach the peak here. And then I slowly start to fall back to earth and pick up speed as I get there. And then for a second, I'm just going to stay on the ground. So like that. And then I'm going to make my second jump, which also will be about 3 inches in a second. And then when I get to the ground, I'm going to stay there for a second. And then I'm going to make my third jump. And that's going to look something like the other two, hopefully. And then I'm going to stay on the ground. So something like that, jumped in the air 3 times, what might be the elevation versus time graph, could look like that. It takes me a second to jump up to 3 inches and come back to the ground. Stay there for a second, jump again up to 3 inches, etc. All right, number 2. Assume that a bacteria population doubles every hour. Which of the following 3 tables of data with X representing time in hours and Y representing the count of bacteria could represent the bacteria population with respect to time? For the chosen table, the one that we choose, plot the graph of that data and label the axes appropriately with units. Okay, well, I'm just going to check to see which one doubles every hour. So my Y value should double every hour. So at times 0 hours, I have 4 bacteria. My 1 hour goes by. This should be an 8, and that's not. And then this should be a 16, and it's not. So I can see right away that A is out. They're not doubling. Looks like we're adding 4 bacteria every hour, which is not what we're looking for. Because B is the right answer, I'm going to skip to C. And after 1 hour, goes by, 1 does not double to equal 3. This should be a 2. That should be a 2. And then this should be a 4, and then an 8, and then a 16. So this one is also out. Let's check this one. As 1 hour goes by, my 3 should double to 6. It does. As another hour goes by, my 6 should double to 12. It does. And 24, 48, 96, 192. It continues to double. So B is the proper graph. And then we just have to label our axis and plot the points. So let's start with our x value. That's time. So I'm going to put time down here on our x-axis. And it is in hours. So we're measuring the time in hours across the x-axis. The y-axis is going to be the number of bacteria. Okay, scoot that in there. And then I need a scale. I've got a scale for my x-axis, but I need a scale for my y. So here's how I'm going to calculate that out. My biggest y value is a 192. And the number of spaces I have available are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 spaces available. So I'm going to divide by 10. 192 divided by 10 is 19.2, and I'm just going to round that up to say approximately 20. So every line of my graph is going to be worth 20. I can't fit all those numbers in there because it's so small, so I'm going to go 20, then a 40, 60, then 80, 100, then 120, 140, then 160, 180, and then 200. Okay, so I can plot my points now. And my points are 0, 3. Well, that's pretty much at the bottom of our y-axis. 1, 6, also very close to the bottom of our y-axis. That's probably too high, but it's somewhere in there. 2, 12. Well, 12 might be halfway, a little over halfway to 20, which is that first line. So maybe right in there, close to it. 3, 24, that's a little bit over that first line, so maybe right there. 4, 48, well, it's beyond 40, but not to 60, obviously, so it's going to be barely above, maybe right there. 5, 96, well, that line between 80 and 120 is 100, so it's just barely under that. So maybe right there, yeah, close. And then 6, 192 is almost 200, so 6 and almost 200 is about right there. And there is our exponential graph. Not too bad. Number 3. Suppose the researchers collecting data for water consumption during a typical school day collected data throughout the night as well. Number 3 is, for the period of time, from the period between the time the last person leaves the building for the evening and the time of the interval of the first person arriving the next morning, how should the graph of water consumption appear? Well, remember, during the school day, we had, some here, and then we had some spikes, and then another spike, and then maybe we thought that was lunch, and then a little bit here, and there's another lunch, and then class period, and a class period, and maybe some after-school things. And then when everyone leaves, it should go down to 0. So if that's our line, 0. Let me actually use a straight line so we can think about this for real. Okay, if that's my x-axis, then when everyone leaves school, there's no one left, no adults or let's say humans, no humans left in the school, then there shouldn't be any water consumption. So our water consumption should go to 0, and it should stay there. Should stay at 0. until the first humans return back to the school and we start that process all over again with water being used in between classes, at lunch, etc. So the time period that we're talking about should be a straight line, should be at y equals 0. Y equals 0. Okay? Number 4. Suppose the researchers see instead, from the time 1:21 a.m. onward, the graph shows a horizontal line of a constant value 4. So a horizontal line at y equals 4 would mean that water is being used, 4 gallons are being used each minute. And that would suggest some possible things might be a pipe burst and we're leaking water, or someone left a faucet on at 1:21 a.m. and left the school, or something where water is being used where we wouldn't expect it to be used. Probably a pipe bursting is the most plausible explanation. Okay, so we might have that flat line. So again, if we had our XY axis, then our flat line would be happening, and then at 1:21 it might jump up here to 4 and then just stay. And that means something happened. Something happened at this point that started water consumption. Maybe the toilet's running. That could be a possibility. Something happened where water is beginning to be used and is being used at a constant rate. Number 5 and 6. Maya and Earl live at opposite ends of the hallway in their apartment building. Their doors are 50 feet apart. Each person starts at his or her own door and walks at a steady pace toward the other. They stop walking when they meet. They stop walking when they meet. Okay, that's important. Maya walks at a constant rate of 3 feet every second. And Earl walks at a constant rate of 4 feet every second. Graph both people's distance from Maya's door. All right, so I'm going to use, first we're going to get some scales, so let's do that. We know that our x-axis is time. And it's going to take probably just a few seconds. If we're walking at 3 feet every second, then 50 feet would get there at around 17 seconds or so. And if we're walking at 4 feet every second, then 50 feet would come up at around a little over 12, so 12 seconds. So it's going to be less than that. So I think we can count by ones down here for time. 5, 6, 7, 8, 9, 10, 11, 12 seconds. I'm sure we're going to meet before then. Okay? The y-axis is going to be distance from Maya's door in feet. Okay, so that's our y-axis. And then let's use a red line for Maya, and we'll use a green line for Earl. Okay, so let's talk about Maya first. How far is Maya from her own door at 0 seconds? Well, she's 0 feet from her door, so that's going to be at the point 0, 0. Oh, we need 50 on here, don't we? So I want 50 to be on my y-axis, and I have, so that's a 50 is going to be my biggest y value. And I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So 50 divided by 20 is going to be 2.5. 2.5. So every line is worth 2.5. Yeah, that's fine. I can do that. So let's get rid of these. And every line is worth 2.5. That means every other line is worth 5. 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. All right, so there we go. So back to Maya. She is going to walk away from her door. Oh, so that distance away from her door is going to be getting bigger. And that's going to be 3 feet every 1 second. So 3 feet in 1 second is going to be, I don't know, about right there. After 2 feet, she'll be at, or after 2 seconds, this is in seconds. After 2 seconds, she'll be at 6 feet. So that's going to be about there. After 3 seconds, she'll be at 9 feet. And that's going to be somewhere in there. 4 seconds, she'll be at 12 feet. So 12 is going to be about there. After 5 seconds, she'll be at 15 feet. And there we've got our first intersection. So that's going to be our line. And we can draw that line in red right through all of those points. And it will continue, so I'll continue it for now. And then let's talk about Earl. Earl we're going to make in green. Earl starts 50 feet away from Maya's door. So at 0 seconds, he's 50 feet away. And he is going to get closer. So his distance away is going to decrease by 4 every second. So 4 feet after 1 second, 8 feet after 2 seconds, etc. So after 1 second, we're going down to about a 46, which is going to be somewhere in there. After 2 seconds, we'll be at a 42, somewhere there. Okay, after 3 seconds, it will be 12 down, so about a 38. So somewhere in there. After 4 seconds, that'll be 16 away from 50, so about a 34. So that's going to be just somewhere in there, right there. Okay, and after 5 seconds, it'll be 20 feet away, so that would be down to the 30. So that one's at that first intersection. All right, we can draw that line in green from the 50 at 0 seconds, and we get something like that. I don't know if we're going to be off a little bit. I don't know. Let's go right on those dots and see what we got. Okay, so something like that. And then the intersection is where they will meet. And they actually stop right here. So as time continues to go by, both lines will go in this direction. But when do they meet? Well, they meet right here. So that's about times 7. And height, I don't know, 21, something like that. Okay? And remember, the graph is going to get us close. After 7 seconds, they're both going to be about 21 feet away from Maya's door. And that's this graph, okay? Number 7. Here's an elevation versus time graph of a person's motion. What is the person's highest elevation? Well, the highest elevation would be the point on the y-axis that is the biggest, and that's this 10. So that point right there is the highest elevation, and it is 10 feet. And it happens at 8 seconds. So we can see at 8 minutes, 8 minutes, we're at 10 feet of elevation. Number 8. During which time interval is the person's elevation increasing? Well, there are 2 areas where the elevation is increasing. This first one is from the time, let's get a straight line here, from time 0 through time 2 minutes. That is an increasing elevation. During that time period, 0 to 2, we go from 0 feet of elevation to 6 feet of elevation. So the first time interval is from 0 to 2 seconds. That's a period of increased elevation. And then there is one more, and that is here, from 7 minutes to 8 minutes. Between 7 minutes and 8 minutes, we go from 2 feet of elevation to 10 feet of elevation. So we also have from 7 seconds to 8 seconds, that interval. That's also a period of elevation increasing. Okay, number 9. During which intervals is the person's elevation decreasing? Well, that's when our elevation goes down. So that's happening from 5 seconds to 6 seconds. And I see it happening again from 8 seconds to 12 seconds. So there's our answer. From 5 to 6 seconds, that is a decreasing elevation. And then from 8 to 12 seconds, that is a decreasing elevation as well. All right, last one, number 10. During which of the following intervals is the person's elevation constant? We have 3 of those, and that is between 2 seconds and 5 seconds. Elevation does not change, stays at 6 feet. From 6 seconds to 7 seconds, the elevation stays at 2 feet. And from 12 seconds to 14 seconds, the elevation stays at 4 feet. So the answer is from 2 to 5 seconds, from 6 to 7 seconds, and from 12 to 14 seconds. And that is the answer to number 10. All right, hope that helps on the review, and we will try another one tomorrow. See you next time.